Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Ragnhild Lunnan with us today.
Happy to be here.
And I apologize for my very poor Norwegian.
That's all right.
Ragnhild, what's your geolocation? Where are you at?
I am in Stockholm, Sweden. So I'm currently a Marie Curie Fellow at Stockholm University. And actually in April, I will be transitioning to an assistant professor position here. So it's very exciting.
Well, congratulations.
Thank you.
Congratulations. That is awesome. So is Stockholm far enough that you see the aura, the northern lights?
If there's been a particularly spectacular solar storm, it can happen. We generally have to get a little out of the city just to get out of the
ambient
light pollution, basically.
But you are far enough north.
Yeah, I mean, you want to be further north for the lake to see them regularly. But yeah, they do happen here every once in a while.
Yeah. Well, it's still on my bit bucket of things to
see. Oh, really? Oh, yeah.
Yeah.
Well, once we can travel again, just yeah.
And toward the end of 2021, maybe. Hope so. Good. That'd be awesome.
Yeah.
So Ragnhild, what do you like to do for research?
So I like dying stars, specifically the exploding kind, supernovae, and I mostly like the weird ones. So that is to say, in the past decade or so, with all of these big sky surveys, we're finding all sorts of interesting stellar explosions that don't fit into these common types of supernovae or type 1As or your normal core collapse supernovae. So I like all the strange ones, and I've worked on several different kinds, but really my main focus have been this class of objects called superluminous supernovae. So these are things that are, it's in the name, they're very luminous supernovae. They're sort of 10 to 100 times more so than your standard core collapse supernova. And what's really cool about that is that means you can't explain them with the same physical mechanisms, basically. So you need some other way for you to figure out how can nature make an explosion this bright. So I think that's very cool. And I'm an observer. So I've worked with a number of transient surveys throughout my career, Pan-STARRS as a grad student and as a postdoc. I went to work with the Palomar Transient Factory in California, which has now transitioned or upgraded really to a much bigger camera and is now the Zwicky Transient Facility. So that's what I'm working on at the moment and what we will be talking about today, I believe.
Cool. So that'll probably take us to this really lovely article. Life was simpler when there was only two categories of supernovae. So you are responsible for this plethora.
Hey, it's nature who put them there. We just study them.
And we have 4 super.
Yeah. So I'll get into where the super is in parentheses. But yeah, so this is a paper about 4 very luminous supernovae that we found right at the beginning of ZTF. And so actually all of these are from the sort of commissioning science validation period. And in many ways, this paper is but a teaser for all of the exciting superluminous supernova science we want to do with ZTF. But we realized, this experiment is going to be very, very good at finding them. During commissioning, we weren't even particularly looking, they're just there. And we found, well, these are, as we'll get into, several of these objects that happened to be the first ones we found were also kind of unusual. So this paper is, on the one hand, just wanting to present and discuss those objects in the context of superluminous supernovae and get that data out there. And then we also talk about, the implications for looking for superluminous supernovae in these big surveys, basically, and the kinds of things we can do once we have a much bigger sample, which ZTF, in fact, has provided. We just haven't published it yet.
Cool.
So
I'll make one side comment here. the common nomenclature to get a little bit unwieldy, right? Because or when there were less than 26 supernovae in a year, it was perfectly great. We have triple, or sometimes even more letters after it. So
yeah, no, the ZTF names are really unwieldy. Actually, like when the survey was starting, we realized, because every alert from ZTF gets every sort of unique sky location where something goes boom, and this not just real transients, but anything that the pipeline triggers on. So variable stars or ADN flares or anything will generate a ZTF alert, and those get a unique 7-letter string, right? And even internally, like I worked on this, so I could talk about these as like AAPGRXO, but that's not going to be very practical for this chat. So I'll probably refer to them by the IAU names, which is 2018 BYM. But yeah, even there, we got into 4 letters in 2020.
Yeah. So we may need some sort of a little bit better classification there. But anyway, that's another topic. Anyway, on you go.
Sure. Yeah. So if you want, you can maybe scroll down to figure 1. Which I believe just shows the light curves, which really, I think, is a nice starting point for discussing these objects. Even actually just getting to this figure was somewhat of a struggle because, at the beginning of a survey, like your photometry pipelines are still being tweaked. Anything that exploded in your first months, there's going to be supernova light in the templates. So figuring out how to subtract that out, etc., is going to be hard. But in the end, it worked really well. And so we have these 4 objects that just really happen to be the first 4 hydrogen-poor superluminous supernovae. And so what you see here are their light curves, luminosity versus time, in different filters. The G and R filters are mostly the ZTF data. And then there is additional data. We have some UV data from Swift and also some GRIZ data from other telescopes, mainly the Liverpool telescope, actually in this case. And on the on the left-hand y-axis, you see the apparent magnitude. I think in these plots, G band is the one that's not offset in each, and then you have the approximate absolute magnitude on the other side. And so this is where we can get into why is the super in parentheses, because you mentioned we have so many types of transients. It used to be easy. We don't even quite agree on what constitutes, say, a superluminous supernova. Where do you draw the line, right? So initially, when it looked like there was sort of a nice separation between normal stripped envelope supernovae and these, and there was like a nice wide gap, it was suggested, let's draw a line at absolute magnitude minus 21. But I mean, you will see just looking at these that actually only the first one gets to minus 21 in absolute magnitude of these ones, for example. And I will argue they still belong in this class of superluminous supernovae. So actually out of these 4, it's only the 2018 BYM in the sort of top left corner that's maybe looks the most like a canonical superluminous supernova. It has a fairly long rise time, 40 days or so, just wide light curve. It has a peak magnitude brighter than minus 21. It sort of fits in with let's say, the more standard examples of the class. The next one, 2018 AVK, I would say is also fairly standard, except it's, it reaches sort of minus 20 absolute magnitude, which is much brighter than a standard core collapse, which reaches maybe minus 18. But it is less extreme, let's say. And it's an example of a supernova that's slowly evolving, but not that bright, which we'll get to, is a little rare in this context. But the truly stunning events of these 4 are actually the 2 on the bottom. So 18 BGV, this one has a beautifully sampled light curve from ZTF. You can see here we have daily cadence data. And what we do is we capture the rise really well. And the rise in this case is actually, it is not 40 days. It is not unusually long. It is actually really, really fast. It's like 10 days, less than, that's faster than, say, your standard type 1a supernova. And this is quite interesting because, and I'll get into this, and we discuss this in detail in the paper, but because the canonical wisdom is sort of superluminous supernovae are slow, it is surprising to find something like this, perhaps, but it also really makes you worry. Have we been systematically missing them because we thought they were all slow?
Right.
And how many objects like this are there out there that we just never took spectra of? So yeah, this object is very interesting in this context. And then this object over here, where, and actually the filters are not offset at all here. You might say, well, okay, so it's fairly slow. That's like a 50-day rise time. So that's no ordinary 1A supernova, but that reaches like -19 absolute magnitude. So why am I even calling this one superluminous? Mm-hmm. And you'll also notice the color is very red. So these filters are not offset. So you can just see that's a G-R color of like more than a magnitude. So what we think this is a example of a dust extincted superluminous supernova, which is also actually fairly rare. We have seen that they tend to explode in like these dinky little dwarf galaxies with very little dust. So that's another of these like canonical wisdom things, right? These just don't tend to happen, or very rarely happen in these like massive galaxies with lots of dust, but this could very well be one. So
I do have one question.
yeah.
Normally the phases put, it's sort of peak.
Mm-hmm.
And so how is peak sort of defined for ADK here? That looks...
Yeah, so I think this one is, so we did K-corrected G-band peak. So it's possible that one was K-corrected from the R-band into the G-band or something like that, yeah. Or that once you actually put in the K-corrections, actually, that one is hard to set the peak because I think actually it is the G-band light curve, but it's just very flat and it sort of has two little mini peaks when you do the...
Right there, yeah.
Yeah, like, do you put it there or there? So in that case, yeah, you could have put the... and it is somewhat arbitrary, right? You fit your favorite regression or whatever through the points and you find the peak. In this case, we used Gaussian processes. That's where it says, but it's entirely possible. Had I chosen a different way to smooth through it, I would have gotten a different peak epoch. Okay. So in this case, the R band and G band sort of agree that, well, it's a very flat, you could call it a plateau even. So yeah, it's not obvious.
Oh, good.
Yeah.
Very cool. And the S's here, epochs of spectroscopy, I take it?
Yes, that is correct.
Okay.
So in fact, if you want to scroll to the next figures 2 and 3, I think they're next to each other in this. Then you'll see our series of spectra, which is how we generally classify supernovae, right? It's based on their spectroscopic properties. And we're trying to move towards that when it comes to superluminous supernovae as well. There's a massive paper by Robert Quimby going through sort of spectroscopic properties of superluminous supernovae and arguing, yes, you can classify these based on the spectra. You don't have to put in any arbitrary luminosity cut to distinguish them, actually. So this figure on the left shows the spectroscopic sequence for 3 of these objects, BYM, AVK, and BGV. These show spectral features that are fairly typical of hydrogen-poor superluminous supernovae, I would say. So on the right-hand side, figure 3, you see some comparisons. So there's one epoch of each supernova shown on the top compared to this sort of canonical supernova PTF09 C and D. You see this sort of W feature around 4,300, 500 or something angstrom that we think comes from oxygen 2. And you see that clearly also in these other. So spectroscopically, you know, those top two look like a blue superluminous supernova, if you want. Now, generally, you know, these objects then expand and cool, and as they cool, the spectra turn redder, and you see sort of different features. So we often talk about the sort of hot photospheric phase and the cool photospheric phase. This other object, 18AVK, we didn't catch it in the hot photospheric phase, so that's the spectra we have of that are generally a bit redder, but there's still a very nice match to superluminous supernovae in this cool photospheric phase. So you can see a comparison to this very well-studied object at 2015 BN just above. So, you know, spectroscopically, I would argue that these three objects definitely resemble typical superluminous supernovae. And I mean, it is interesting that even this BGV that was very fast does show this very typical oxygen feature in the beginning. Yeah. So the fourth object, the one with a really red and kind of bumpy light curve, is a bit more complicated. So that's then not actually shown on this figure. It's shown on the next set of figures. Yeah, 2018 DON. So I think my view is lagging a bit, but yeah, there it is. So the top just shows, so figure 4 just shows the sequence of spectra that we have that actually show extremely little evolution. Overall, you see more or less the same features over this time period, and they're kind of typical supernova type 1 features, I would say. We see oxygen, calcium, iron, magnesium, some silicon. And if you take this spectrum and you run it through one of these like supernova cross-matching codes, like SNID or SuperFit or whatever people use to classify supernova, you will get matches to type 1 supernovae in general. So both type 1a and type 1c supernovae. But I would say the light curve very clearly rules out a type 1a supernova interpretation. Those are wonderfully standard. They rise in about 2 weeks. They have this nice, well-defined decay and colors and all of those things. And this light curve looks nothing like that. But the spectrum also doesn't look like these very blue objects that we just discussed. So what does it look like? Well, if you scroll down a bit to the next figure, figure 5, you can see that it actually looks quite a bit like this famous superluminous supernova 2007 BI, but only if you allow for some host galaxy reddening. So you see on the bottom, the observed spectrum, that's actually a stack of the other ones, and that looks pretty red. But then the spectrum above it has been de-reddened by EB minus V of 0.4 roughly, and then you get then you see actually this matches quite well both features and continuum with this supernova 2007 BI. So, you know, I would argue that that is the best explanation for this, that it is a superluminous supernova, spectroscopically similar to this one, and it's just heavily reddened. So if we think back on, you know, this peaked at like -19 or something, absolute magnitude as observed, but with this amount of host galaxy reddening, that's more than a magnitude. That's about a magnitude and a half in G-band, a magnitude in R-band. So that actually brings it into that like -20 and a bit territory. So that makes sense.
Do we know that they're not self-reddened?
So you mean they create their own dust, basically?
Yeah, there's some pre-explosion eruption that then dusts out and then you get the explosion?
So I guess we don't necessarily know that, except in general, these are such energetic explosions that we would think most dust close to the supernova would be destroyed by the supernova.
Okay.
And that's especially true for these superluminous supernovae that are generally much more UV bright than other supernovae. So that means they kind of obliterate all of the dust out to a bigger distance. So if the dust came from the star itself, it has to be fairly far out, basically. And no, but it's an interesting point. I was discussing with another postdoc here at Stockholm, Mattia Bulla, who's done work with type 1a supernovae, trying to figure out, you know, is the reddening coming from ISM or CSM, basically? And with type 1a supernovae, it's easier to figure out because they have such standard colors. And then you might look for very nearby dust in things like light echo effects.
Right.
And the problem with repeating this kind of analysis for superluminous supernovae is that these are, you know, they don't have standard colors in the same way and like standard behavior. So it's much harder to detangle kind of what is intrinsic and what might be coming from. But it's not a bad question. Anyway, so based on their spectra, I would argue that all of these, and I do argue, that all of these four objects are superluminous supernovae, at least in this spectroscopic definition. And they are, you know, are also actually, when accounted for reddening, much more luminous than ordinary supernovae. So sort of with that established, in the rest of the paper, we both put them in context of the general population and then talk a bit about what might be powering these objects and then finally get to kind of implications. So if you want to start with the context, we can maybe move to figure 6, I think it is, which
Rise time.
Yeah, exactly. It shows the timescales and absolute magnitudes, basically, compared to a sample. In this case, the sample from the Palomar Transient Factory, which, you know, was conducted from the same site with the same telescope, actually, as ZTF, and therefore, you know, went to a similar depth, finds things in roughly the same redshift range. So where it's somewhat of an apples to apples comparison in that sense. So all of these background points, open circles, are the PTF sample, and then these colored points are my objects. So on the left-hand side, we have rise time versus absolute peak magnitude. And yeah, the 2 points spaced vertically for 18 DON is basically whether or not you take into account the reddening. So with that assumed reddening, that brings it up to the higher point. And so the green point, 18 BYM, is the object that I said was kind of, this is the most vanilla of the 4. This is the one that kind of sits in the typical part of parameter space, both in terms of its timescales and luminosities. The blue point, 18 AVK, is, as I mentioned, it's an example of one that's both fairly slow, but fairly, well, it feels strange to call something faint in this context, because sort of by definition, they're not faint, but, you know, I don't know. I heard someone say like underluminous, superluminous, and it's like, no, let's not go there. But yeah, that's where, you know, that sits in a part of parameter space where there aren't a lot of examples, actually. And you see that also on the decline time scale on the right-hand side. It's also kind of a little bit by itself in this faint and long-lived. So that's interesting.
Yeah.
And the reason why you get this huge error bar for 18DON here is because of that big bump in the on the decline of the light curve.
Yeah. Okay.
So, you know, when you try to interpolate through that and you look for what's my decline, it's like, well, my error bar stretches from here to like 20 days later, because I guess it depends on whether you think that sharp drop is part of the, whether you count that as like the decline time scale, or whether we can look at that light curve again in a bit.
So you want to go back?
Yeah. No, that's okay. We'll get. Oh yeah, we could. You can scroll back to it.
We'll go back to figure 1. Let's light curve again. There we go.
Mm-hmm. Yeah. So you see, it has a slow rise to peak, and then a fairly sharp drop, and then it sort of plateaus again and drops. So like that's why it's hard to, you know, in this case, I think. I don't even remember, but it says so in the text, whether we used 1 magnitude below peak or like 1 e-folding time or something, but you know, some fixed fraction from peak. And so, you know, in practice, just like drawing a line here, and you can see that line ends up being more or less like where that plateau is, which is why you get that big
drop.
Yeah, that big error bar basically on what is my decline. Yeah.
Okay.
So, yeah.
Yep.
And of course, the final interesting or sort of unusual object is the yellow point, which is actually the shortest time scale, especially shortest rise time superluminous supernova ever discovered. And I mean, there is a point kind of next to it, and we'll see what that light curve looks like in the next figure, sort of for comparison. Actually, we can probably move to the next figure 7. Yeah, so in the bottom left corner is 18 BGV again. And here, compared to light curves, are sort of the most similar objects I could find in the literature. So I think that blue object is that PTF object that had a almost as short rise time, but you can also see that rise time is not nearly as well determined as it is in this case. Like we really see this sharp rise. So that is very unusual. Decline-wise, it is not as unusual. You can see there are a couple of objects in the literature with that sort of decline and similar-ish peak magnitudes. Yeah, so I guess this figure in general is putting them in context in a slightly more detail, not just looking at quantities derived from the light curves, but actually comparing the light curves themselves. So again, the top left is 18 BYM with a couple of similar timescale, similar luminosity objects. You can see in the next plot, 18 AVK. Actually, so light curve shape-wise, it is not that unusual. And there are a couple of objects like it out there as well. So, you know, it is not unique in its faint and long-lived. It's just not the most common thing. And again, it's interesting to ask how much of this is observer bias versus intrinsic population, because it's things that are both very luminous and very long-lived are the easiest ones to find, basically. And things that are faint are harder to find. So,
faster.
Yeah, at some point, people were getting very excited about the possibility of like standardizing superluminous supernovae, because they're the, you know, sort of by definition, they are the most luminous supernovae. Which means you see them to the furthest distances. And imagine how cool it would be for cosmology, say, if we could use them the same way we use type 1a supernovae. And, you know, there are attempts to do it. They're certainly not as standard as 1A supernovae, but there are, people try based on combinations of colors and time scales and all sorts of things. And we always seem to find objects like this one that just don't fit those relations, basically.
Okay.
Yeah. Let's see, we already talked about 18 BGV and its beautiful sharp rise. Yeah, and then the final panel here is showing again 18 DON with its sort of weird bumpy light curve. And I mean, the thing is, like, as you can see, light curve bumps are not entirely unheard of in these kinds of supernovae. There's a couple of examples here. This very well sampled 15 BN was a much brighter object, but otherwise had kind of, this red light curve, sort of similar timescales, and a bump, a much smaller bump, but a bump that's a similar, yeah. And then there's this IPTF 15 ESB, the blue light curve. We didn't sample the rise, unfortunately, but you can see it has like a series of bumps on the decline. Yeah, and there's also this yellow object from Pan-STARRS 12 CIL, which also, again, has a fairly pronounced second bump. Where that one's different, though, is, you know, there we do sample the rise, and there it's kind of clear the rise and immediate decline sort of have similar timescales, whereas 18 DON has kind of a slow rise and then a sharp drop, which looks pretty different in some sense. Yeah, so yeah, so there, yeah, especially these two on the bottom are fairly unusual in the context of superluminous supernovae. This is looking at the supernova properties. We also took a look at the host galaxy properties briefly. So, you know, the other way to, or another sort of perspective on what's going on can be to look at not just what does the explosion look like, but also what kind of environment did it explode in? What kind of stars do you find in those environments? And I guess we can go down to figure like 13, I think is the just galaxy summary figure. So it's been known for a while that generally superluminous supernovae tend to prefer low mass host galaxies, which is often interpreted as a metallicity effect. So this was one of the main results of my PhD thesis, actually. And I mean, not uniquely so, but generally so. And so what we have here are same color scheme as before. These various open circles are galaxy the literature sample in this redshift range, basically, from different surveys. So we just see as a function of redshift a scatter plot on the x-axis versus the stellar mass. And most of the superluminous supernovae are found in galaxies of less than 10 to the 9, basically. So sort of 10 to the 7 to 10 to the 9 dwarf galaxies, with a couple of exceptions. And 3 out of the 4 objects here are in those kinds of galaxies, basically. And the exception is this 18 DON, the one that we think is reddened. So that is in a more massive galaxy, as far as we can tell, and also consistent with having a reasonable amount of dust. So basically the kind of extinction we derive from comparing the supernova spectra that's consistent with the galaxy SED. So at least the story holds together. Of course, you don't know exactly where in the galaxy the supernova exploded, etc. But if it was in a like strikingly blue, extreme like dwarf starburst with like 0 evidence of dust anywhere, that would be weird or weirder.
Fortunate or unfortunate, depending on your point.
Exactly. So this sort of This makes sense. And of course, it again points to why it can be hard to look for these things, because you, again, kind of have to ask yourself, it's fairly easy to find a very bright transient in a fairly faint galaxy. Not that, we're not good at finding transients in all kinds of galaxies, but we're more likely to realize those are unusual in general. Mm-hmm. And so, again, one way people have suggested we can look for superluminous supernovae is to look for transients that are like X magnitudes brighter than their host galaxy. That's one parameter space many of them stand out in, but again, looks like that's not sufficient basically to catch an object like this one, for example. And how biased our various surveys are, who knows?
Yeah, we don't know.
Again, that's why this is hard.
Yep.
Yeah. So
cool.
That sort of establishes much of the context of what these objects are, or how these first ZTF objects fits into the general picture. So in the rest of the paper, we mainly, first of all, discuss what kind of models might fit them, what might be the explanations, with a special attention to these two strangest ones, DON and BGV. I guess maybe let's jump back to figure 10, which shows, I believe, the
B fields.
Some results of some model fits. So there's
Magnetars. Okay.
Magnetars, yes. Magnetars are extremely fashionable in the transient world right now, because they are so wonderfully flexible.
Yeah, how about that? Yes.
Yeah. No, but actually, I mean, they are one of the most popular explanation for superluminous supernovae. So as such, it is a useful exercise to see how well are these objects fit by a magnetar model, and how do they sort of compare to the general population. And you can see 3 out of the 4 kind of land on the general locus of this literature sample from Matt Nicol. So this left side plot is the derived magnetar initial spin versus magnetic field. Mm-hmm. And then on the right-hand side, you have spin versus ejecta mass. And yeah, you see the 3 objects, basically apart from the one that stands apart is BGV, the really fast one. So that one can still be explained in a magnetar model context. You can find a magnetar model that fits it, but it has to be kind of different from the one that fits the other ones. And in particular, you need a fairly low ejecta mass. And this makes sense because if you want to make something rise really sharply, you need a short diffusion time, basically. Right. So that's what's driving that. DON, you can fit the sort of overall properties of the light curve. And what's not shown here is, like in this plot, is the extinction that the model lands on. But yeah, if it wants to fit this as a magnetar, again, you need like a couple of magnitudes of extinction, which makes sense because magnetar models are hot and blue and this object is red. So even for this very fast one, a magnetar model can work. And I mean, there's nothing to say that, so the yellow one is the very fast one. There's nothing to say nature can't make a magnetar with those parameters. But this sort of 10-day rise time is also in a kind of interesting part of parameter space where you're starting to inch towards what some people call luminous blue transients, or fast blue optical transients, sometimes FBOTs, speaking of new types of things. So, usually when people talk about FBOTs, they mean things with like rise times of a few days, not necessarily 10 days, but it's sort of moving very much in that direction, let's say. So, you know, in addition to this magnetar model, we discuss a couple of other potential mechanisms for a transient like this one, whether it could be CSM interaction, or there's some scenarios with like an ultra-stipped star in a binary and a pulsar wind nebula. So like still an engine, but a different kind of engine. And I mean, I guess to really nail it down, I think you're going to have to do a bit more detailed modeling than that's sort of within the scope of this paper. But what's really cool is we have this very nice data set. You know, we actually have this beautiful light curves and series of spectra that also gives you constraints on the velocities, etc. So I really hope someone will pick up this challenge actually and really try and model this object. And then the other one that we discuss in a bit more detail is this 18 DON with the bumps, because, you know, I sort of show here like, yes, you can find a reasonable magnetar model that sort of fits the overall shape of the light curve, but what a magnetar cannot give you, what nickel decay cannot give you, what any of these like smoothly decaying things cannot give you is a light curve with these like really sharp variations. So we speculate whether this could be an object with basically circumstellar interaction either on top of a underlying engine like a magnetar, or even have the light curve being powered by it. And the comparison to this other really bumpy object, 15 ESB, which we saw in one of the previous figures, I think. I guess we can jump back to figure 7, maybe.
Yep.
Anyway, that is a, yeah, that blue light curve there with a series of bumps. So that was a object that later showed kind of direct evidence of CSM interaction, in that at late times you started to see this booming H-alpha emission, showing that the supernova had in fact run into some shell of material. And there's increasing evidence in multiple ways of, you know, basically seeing superluminous supernovae with circumstellar material around them, which is not necessarily saying that the entire light curve is powered by circumstellar interaction, but it's at least saying that there is, you know, it's a messy environment. So we wonder whether that could be at play here. But again, it's not the only thing that could explain it. If you have a central engine with that, for example, like launches some jets that don't quite break out, that kind of thing, then you can have, there could be angle effects that give you this kind of sharp drop, etc. Like, you know, there are other things out there. And again, I really want people to, you know, take this light curve and go crazy in modeling it, basically.
Love that appeal. All right.
Yeah, it's a challenge.
Good.
Yeah. So yeah, that's basically it's towards the end we talk about just as I've alluded to multiple times. Well, you know, it's clear superluminous supernovae are a fairly diverse population, and that makes it hard to devise a strategy to pick them out in a survey, for example. So, you know, basically filtering on any one attribute, like say light curve timescale or host galaxy properties, or so like you're gonna miss something. So yeah, it is hard, and we conveniently defer all of this problem to a future paper, which Dan Purley is working on, where he will talk about the strategies for finding superluminous supernovae in ZTF, because it turns out, you know, these objects were found during science commissioning, which was like the beginning of 2018. So now we're like 3 years in, and, you know, rather than these initial 4, we have a sample of like 60 or 70, somewhere in there, hydrogen porous superluminous supernovae, and about as many hydrogen rich ones. So there is a whole lot of exciting work being done on that. You know, there's a sample paper in the work written by Geo Location, you know, presenting the sample. There's the selection paper I mentioned by Dan Purley. There is a rates paper coming that Lunnan is working on. And, you know, there's various subsamples that are really interesting. Like we already published, as I actually letter, I think, a subsample of hydrogen poor but helium rich objects, superluminous supernovae, which kind of there, I think there was one example before, and now we show actually this is like a whole its own little subclass. There's more of them. There's, you know, interesting individual objects. Yeah, so it's a very rich data set. It's very exciting.
Indeed. Very cool.
Yeah.
Yeah, so the future is got lights on the pipes on these category busters.
And I mean, this is the really fun thing about having a basically all sky, well, all northern sky survey is you find almost everything. And we even have had this, you know, concerted effort to classify everything above a certain apparent magnitude. So having a, you know, at least a subsample that is spectroscopically complete, which makes evaluating all of these biases and looking at sample properties, etc., a lot
Are there any
easier.
plans, do you know if anybody's doing any plans to do something similar in the Southern Hemisphere?
That, I mean, there are,
I'm just curious.
yeah. I mean, there are surveys that cover the Southern Hemisphere, like Assassin, for example, though they don't go quite as deep. And of course, LSST is going to be what covers the Southern Hemisphere, like, you know, basically the sky coverage of ZTF, but going magnitudes deeper. So that's, you know, that's basically, in many ways, ZTF is sort of a stepping stone survey for the community, going from like these smaller surveys and into the LSST era, and the alerts infrastructure we're using is what will be used for LSST, for example. So it's basically, you know, we're the training wheels, so to speak, for, but yeah, there are, you know, alerts brokers being built for LSST that are currently in use with ZTF data, for example. Yeah.
Cool. Awesome. Ragnhild, I want to thank you so much for spending some time and sharing your lovely paper with us today.
Thanks for having me.
You're welcome. All right. We'll see you everybody on the next one. Bye-bye.
Bye-bye.